Do, 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 do. Do, 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 do. Okay, I guess we're live. Okay, we're live. If you're on, say hi. Okay. All right, let me just check a couple of things. That's good. And that's the agenda. All right. Cool. I hope the font is, decent enough. I think that should be fine. Hi, Lavanya. Good afternoon. Okay, I see folks are joining in. I'll give it another minute and I'll get started. Hopefully I can keep this short and in under 30 minutes. That's the plan today, but we'll see how it goes. Okay. All right. Yeah. Looks like I have everything. Let me just get started. So I hope the fonts are, the font is legible, and I hope, the screen switching is also working. I'm not stuck on some screen, etc. Can someone just confirm that? Right, is the font size okay? Great, I just got logged out of chat. Just give me a minute. Okay. All right, just give me 1 minute. Let me just sort of sort this chat thing out. I think restream is getting very painful, man. Okay. All right. So All right, chat is like messing with it, so I guess you guys can just use Signal or something to ping me. All right, I guess you guys are on Signal, right? Let me just ping you guys on Signal. Hey, let's just use this. Okay. All right, cool. Let's get started because this thing just, wanted to like screw around. Okay, so in the last stream, we talked about, we've been working on the porting rustBoot to basically the i.MX8-M. And let me sort of show you the agenda. So we've been working on porting rustBoot to the i.MX8-M. We've got a working UART console. Then the next step was for us to implement the SD card driver, or in this case, it's called the uSDHC, which is nothing but the ultra secured digital host controller, as i.MX8, as NXP calls it. So we went through a bunch of things in the last stream. We talked about the SD standard. We talked about a high-level overview of the implementation level details in terms of what the SD protocol is, what sort of commands are available to you, etc. We also talked about specific to the i.MX8-M, how do we go ahead and enable things like clocks and counters and all of that stuff. So pin multiplexing, we sort of went through all of that. Today, what we're going to go through is simple. We're just going to look at the implementation alone, where we left off on the last stream. We're going to look at the SD initialization routine. We take a look at some of these registers that are specific. We'll also take a look at how far the driver has come in terms of development, and we'll take a look at things like clock settings and a bunch of commands that are working. And also, how do you debug something like this? Because we now have a working UART console, you'll now get to see, how useful that is. All right. Any questions so far? Okay. Any questions? All right. I guess not. So let me quickly get started on, we'll just directly jump into the implementation itself. So if you look at the implementation, the way this is structured is you click on boards, you look in the hardware abstraction layer section, you'll find NXP, and then you will find the board support package for it, in which we have all our drivers. All right, so this is where this is the folder structure. Now, the last time we implemented a UART, that's how we have a working UART console. Now we also have this particular uSDHC driver. Okay. Now what I've done is I've collapsed all of the most of the implementation, so that's easier for us to sort of go through. So firstly, the way this is I've implemented this is, there's a whole set of registers, about 30 registers for the uSDHC. Now, I've simply gone ahead and used the talk registers crate, which is very good in the sense that you can clearly define bit fields and then use those bit fields. I'll show you an example of them, but just to know, if you just want to look at one of them, here's one of them. So let me show you this. Yeah. So this is one of the registers that, one of the registers is part of in this register block for the uSDHC. And, the most important bit fields are command type, command index, and response type. Okay. So this particular register is how you actually send commands. And you also, sort of explicitly state, I'm expecting this sort of response back, these many number of bits in the response. So that's what, these register bit fields are, as the name suggests. Using those register bit fields, you'll create register you'll create a register block, right? So it looks something like this. I say all of these registers make up the uSDHC register block. Okay, so you can see that there's block attributes, command argument, command transfer type, command response. All of these are just registers, and in the previous macro that we have, wherever we've sort of declared or defined our bit fields, we use that here. So in talk registers, you've got like 4 types. You got the read write register, you got the read only register, there's also write only, which I'm not using here, and there is also read write, read only, and write only. That's about it. Yeah, that's about it. Those are the 4 registers that you have, and these registers, the reason this crate is very useful is because if you actually look at the imports, you will see a couple of things. You'll see that there are interfaces. That means the read writable register supports reading and writing, and you have those kinds of methods only. Say you mark some register as readable only, then you're only able to read it. If you mark some registers as write only, you can only write to it. So only the write specific methods are available. So you don't accidentally end up using a read method where, on something that's only writable, or vice versa. That's why talk registers is, pretty, I wouldn't say it's actually very, very ergonomic. There are some issues with it, but it's the best we have right now, and it works. It works really well. So after I do that, I basically just take this register block and I wrap it in another type. I'm calling that type uSDHC registers. Likewise, these registers, the ones in here, all these are the registers pertaining to the controller that's present on the i.MX8. Now, I also have registers that are present on the SD card, the actual SD card, because I in the last stream I mentioned that it is actually there's a tiny microcontroller within the SD card. When you plug it in, it gets power, and you can access those registers. Those registers are also something that I have included here. So for example, if you were to see something like CID is a register, then SCR is a register, the same registers that we saw the last time. Okay, so I basically do the same thing again, go ahead, define all the bit fields in there, the ones that I want to use, and sort of declare them over here using these macros. Then the next piece that I see over here is I have some constants that I need to use. I will go through what these constants are, but they are constants, they're not big deals. And then here's the most important point. We will be sending commands to the SD card, and the SD card will respond. Basis whatever command depending on what command you've sent, you'll get a response. Responses are of certain types. That means you can have a 48-bit response, you can have a 136-bit response, and then you can have a 48-bit busy response. So there are like 4 or 5 types of responses that are present in the SD standard. Those are what we use. But basically, this is what a command is for me. A command is nothing but, it's got I basically create a local copy of the register so that I set the fields in the register, and then when I want to send the command, I basically copy whatever I've set in this local copy, and I set the actual register. That means I create this local copy, which is like a temporary holder for where I can set the bit fields. Then finally, when I'm ready, I'll go ahead and set command transfer type register. Make sense? Any questions so far? Right. I guess not. Right? Okay. Cool. So that's a command. And now when you look at the implementation of the command set, it's very simple. It's just, I just initialize everything to 0. Basically that. Where do we use these commands? We actually use these commands very specifically. I'm going to skip over a bunch of these types. They're just, when you use them, you'll sort of figure it out. The more important ones are what I'll be touching on. Here is an enum. This is the official list of all SD commands that the SD standard, contains. And it's not the full list. It's just the ones that we need for now for this implementation. And we don't even need all of them. I just, just added all of them because I've been using them for a while. So I've just added all of them. But here are the set of commands that we would send to the SD card, and then depending on the command, the appropriate response or operation will be performed by the SD card. Okay, so for example, go idle state means that I've actually got like a nice little chart over here. This is the actual standard that I've been looking at. So if you sort of consult the standard, you will see that, where is that? Yeah. I hope this is visible. It's visible, right? So this is a detailed command description. There's a lot of information in this document. We don't need all of it. We just need to see that, okay, if you send command 0, it's a broadcast command. That's why it's called BC. The argument, you don't need to send an argument. Whenever you send a command, you can also send additional arguments saying that here's the command and here's the arguments. Now give me a response. For idle state, you don't need to send any argument. You don't even need to expect any response. And what happens is when the card receives this, it's going to basically reset everything and go into idle state. Okay. Likewise, if you see command 2, it says send CID. CID is basically, if you remember before, I said CID is one of those registers that is present on the SD card. You can read the CID information, which will contain things like card ID, card identification information. All right. So the response over here is the R2 type response, which means this is I believe this is a 48-bit response. Yes. Oh, sorry, this is a 128-bit response that you're going to get back from the card. Okay. You're going to get 128 bits back in the response, and you can read it out. Right. So like this, you have a whole bunch of commands that you send and you receive answers or responses to. This is the SD standard, right? Questions? I guess not. This is pretty, simple. Now, with that said, I've come up with the possible list of commands that I need. Now look at the implementation for this. Whenever I want to set a command, or rather actually send a command, here's what happens. For example, let's take, idle state. In idle state, what I do is I basically say, okay, if you're wanting to send the idle state command, so here's how you send it. Go ahead and create one of these SD card commands. In order to create that, basically set the string. This is something that you can set. Remember, I said we can create a local copy, register copy using talk registers. We do that. And then in that local copy, I'm basically going to set the bit fields that I need for a particular command. Okay. And then that's the command that I assign to command code. Now, once this is done, if, for example, I go into something like, the implementation for my uSDHC controller, and if I jump into initialization routines, you will see that I use this method called send command. When I send the command, what actually happens, if you were to just sort of walk through, when I send the command, I'm actually sending an SD card command. What actually happens? It calls something called SD command P, which is another, which is the main sending routine. So we're just creating 2 levels in between because we want to do some filtering and selection, etc. But anyway, this is the main command. We need to sort of send a command. So this particular method sends the command and then handles the response as well. See what happens over here. All we do over here is we basically, we need to do some, timing specific waits over here. We need to wait for something. That means to check whether or not the command and the data lines are free, that they are not busy. First, I need to check that. And then here is where I actually set the registers. See, I say register this, register this. I set the command code over here. Make sense? So all that creation of an enum and then creating that command code for an SD card, all of that is basically so that we can, at this point, we can clearly set the right registers properly. Okay. So yeah. Okay. So that's good. Now that we have done that, so you've already walked through the commands. We've seen that, I've got a send command. The send command actually calls send command P. That means send command packet actually. And then I'm pretty much setting the right registers and then sending the command out. All right. And then there's a lot of timing specific operations, which is why debugging is very important over here. Okay. When you debug something that is timing sensitive, you definitely need like a good way to get the right information. Okay. So with this context, with this much information, I think we can look at an actual, let's actually fire up the board and, run this code on the board and see what happens, right? Let's just do that. So likewise, we just pull up the virtual machine and I'm going to go ahead and turn on my, I hope you can see the VM. It's not blocked or anything, right? Okay, I just have to connect it. All right, so we've connected to the board. That's what OpenOCD is done. Now we'll pull up GDB and basically connect to OpenOCD and start debugging. So before I do that, I just want to check if I have done a couple of things, which is right. So I just compiled my code. Now I'm going to go back, and before I go back, let me come back here. I've already started my serial console, which is already working. So let me connect. So GDB is going to connect with OpenOCD now on port 3333. So that's done. Now I'll just reset the entire board, and then, like I said last time, this is the tricky part where we had to spend some time figuring out why we were unable to disable the MMU, because that's what we need to do before we can get to load our code onto the device. So I disable the MMU, and again, just to confirm that it's disabled, you can see this part. For folks who may not have joined the last stream, this was just a recap. You see that the MMU is disabled over here. Okay, and I'm just going to load my code onto it. So I'll just click this. So I've loaded my code onto it, and we are right now at, the code is being loaded into this address, which is hex 9120000. Okay. Now I simply can go ahead and hit C, continue, so that now execution can start from that point. So if I do that, let's see what happens. Okay. So you see, this is what we have. This part is pretty much from the last session where, we basically got the UART console working. All right. Now this remaining part is what we've just implemented. So this is why the UART console is extremely important, because you have, basically there's a lot of timing sensitive operations that are going on. Also, there's, very fine bit setting that's going on, and you want to be sure that some bits have been set and some bits have not been set, etc. All that stuff. Okay, so let's just walk through what's happening over here. Before that, any questions so far? Should kind of be fairly straightforward. Yeah. Okay. All right. So that's good. So let's just sort of walk through this. Let's sort of look at this, and then let's look at the implementation. Let's look at the debug output and the implementation. So if we just sort of collapse everything again, here's what's happening. If you go to main.rs, you'll see that we are trying to initialize the SDHC controller. That's what we're doing. So either it's initialized successfully or it failed to initialize. In this case, you see, it failed to initialize, which is exactly what we have. This part that's popping up is because of the terminal. I don't know why that's happening, but anyway, that's a problem. We can sort it out later. So it failed to initialize anyway. So there's obviously more work that needs to be done on the driver. But since we've gotten this far, let's actually look at what we've done, so far. So let me pull up this. Yes. So if you actually click, go to the initialization routine, you will see that we first reset the card, and resetting the card, etc. For pretty much for most cards and for most implementations, it's the same thing. You go ahead, there will be a single bit that you'll need to set so that everything is reset, and then you'll need to wait to ensure that that reset has happened, and then you need to clear some interrupts. Then then you'll need to set up the clock. There's some steps that are usually involved in it. So if we were to take a look at the reset method, you will see that this is the process, and it's a little it's a little lengthy, but it's just setting a bunch of registers in the right order at the right time. Okay. The important thing is to reset the complete host controller. What we need to do is this particular register has a bit called the reset RSTA, which is basically the reset bit. So if you set that, then the entire host controller is reset. That will ensure that the card is also reset, in other words. And then you start, you set a bunch more bits, etc. depending on the implementation. Here, what happens is you need to particularly set this, field called initialize active, or if I was to sort of look at it, I would say, initialization active is the particular bit field over here that I'll need to set. So all of this is very specific to different boards. But in a general sense, you see that there are certain steps that you follow, and the reference manual offers most of that information to you. You don't have to break your head and figure it out. They will offer most of the implementation, but it's always useful to look at other existing working implementations to sort of save on time and get things done quicker. Okay, so some of this stuff is already taken from other implementations. All right, so that's one. So this is the reset card. You see that there's no, there are no errors when resetting the system. It works well. So that's good. That's done. Now, after we've reset the card, what we do is, if the reset is okay, if the reset is not okay, then you just basically return. So we didn't get a return, so obviously the card was reset. So that's at least that's successful. Now what we do after that is we basically go ahead and run the first command. This is a very specific command. It's called the op command, op conditions, operating conditions. We'll sort of need to set that, and I'll need to look at this. So when I send that command out, I'm expecting something to happen. Okay. So if you look at this, sorry, let's look at before we go here, let's actually look at the first command that was sent out. When resetting the card, I automatically send out the first command, which is go idle state. Okay. That's the first command that I send out, and I'm actually waiting for a response. So no, I'm not actually waiting. So sorry, go idle does not require a response. We send the command out, and that's it. The assumption is that the SD card has, reset itself and gone into idle state. Okay. So that's happening over there, which is why you see this particular print. Where are these, print statements coming from? If you were to ask me, I will simply just sort of show you that. When I do send command calls send p, so I'll just directly go here. You will see over here that we have I effectively have a logging statement that says, go ahead, every time you send this command out, obviously this will be hidden behind the log feature when it actually is ready and when it's usable. This will be hidden behind a feature. It's not something that you'll be printing out every time. This is only when you want to debug stuff, or rather you might want to hide it behind a debug feature. But anyway, so this is where we know that we are sending the right commands. We can look at the exact command that we're sending along with the command arguments. If you see over here, this is the command name that I'm sending, this is the command code, and this is the command argument. In fact, if you look at the second command, which is the operating conditions one, you'll see that only the last 2 bytes have some, basically non-zero value in it. And that's exactly the places that you need to check. So here's another thing. You need to check these things, because the command code is actually field number 24. If I was to show you the, transfer command, if you actually went here and you looked at the transfer command, you'll see that command index is offset number 24. So offset number 24 is where you are seeing, so the first 2 bytes are 16 bits, and then you have 20, and then you have 24, right? So we are trying to actually set the right bit fields when we're sending these commands out. That's the key point I'm trying to make. That's why when you debug, you need to sort of check all of this stuff, and just to ensure that you're not missing something out, or you're assuming something, etc. Okay. Any questions on this? In terms of the little nitbits about debugging and stuff. Yeah, I think we can sort of complete this, because that's what I wanted to show you. This is how far we've come with the driver. Anyway, I'll be pushing this code out so that you can actually take a look at it. But yeah, any questions? Okay, cool. All right, so that's what's happened so far. So we basically figure out what command we need to send. We send the command along with an argument if need be. Then we wait for a bit to say that the command was sent properly. That's what this command completion thing is. And then we start reading it out and getting a response. Okay, that's effectively what send command does. Now you see that there are 3 or 4 commands over here. All of these are just, filtering. Basically, if I want to send a command without an argument, I use this. If I want to send a command with arguments, that's why the A. And if in the SD standard, there are also commands that you send, the way you send them is you first send something called the application command, and then you send another command. So for those commands, you use this method, right? But all 3 of them ultimately rely on send command P. Okay, that's why you sort of make this a little more easy when you want to debug and stuff. That's why this particular implementation is being used. Make sense? Sorry. Okay, now that that's happened, now that you know how we're sending out commands, etc., now there's some, basically we can actually go ahead and look at the clock. The clock seems to be set fine. The reason you can say that is because let's actually take a look at the way you set the clock. I'll just give you an example because I was doing some debugging. You see this particular line which says frequency set to 25 megahertz. That was not happening. It was actually, sort of some weird values what was being set. The way you set the clock for this particular, uSDHC peripheral is using this register, which is system control. So the way you actually set that is you look at in this case, if you actually go back and look at the system control register, you will find that you'll find these two fields, which is the divisor and the SDC clock FS. So if you click on this is the frequency select fields. But actually speaking, you are going to be setting any one of these values. That means 0 to hex 80. You need to sort of be setting any one of these values. Only then will you get the right clock value. So if you see here, if I set 0 and if I set my divisor, which is the DVS, at bits 16, which is in this case actually the value is 15, but if you set 15, it's going to be divided by 16, and if you set the value 1, it's going to divide by 2. Or sorry, if you set the value 0, it's going to be divided by 1, which is basically just 1. The simple formula is when you start up your machine and when you actually enable the clocks, etc., I'm using a 400 megahertz base clock. That 400 megahertz base clock needs to be, you need to derive a lower frequency clock from it for your actual usage. In this case, you want the 25 megahertz clock. So that is why these two fields are used to set. Now, if you wanted a 25 megahertz clock, the calculation is something like this. I use, I don't know if you can see this, but yeah, let me actually just go back here. You should be able to see this now. So the calculation is I do 400 divided by, actually, so let me just separate these out so it's easier. So divided by 16 times 1. If I do that, if you actually do that, you will get 25. You know what? Let me just sort of double check that. So yeah, if you do that, you basically get 25 megahertz. That's the calculation that I was going for. So this is another important piece. Setting the right clock at the right, at the right time is also very important, and ensuring that you're doing this correctly is also important, because trust me, I've got it wrong and I was breaking my head for quite some time until I figured out that I didn't set it correctly. So these are a couple of small little pieces that I'd recommend that you look at when you're actually debugging something like a uSDHC driver implementation. Okay, so, and then there's not much else to it because the driver is not fully working, because if you noticed, the actual most of the pieces are working, which means the commands are being sent, they are being received, you're not getting any errors, etc. Because if there was an error, I would know, because that's how I've written the implementation. My send command P would throw the error. Let me show you. So let's say there was an error when I was waiting for command completion. Okay. if there was an error, then, pretty much I would end up, doing something like this. I'd end up getting errors like something that looks like this, timeout errors, all of that. But I'm not getting any of that, which means the commands are at least successfully working, but I'm not getting the actual contents. The first few commands that I'm sending very simple ones. I'm saying read the registers that are present on the card. Read the CSD register and give me the output. I'm getting all zeros. Basically, I'm not getting any information back. Because if you see here, I've printed out the entire set of registers, all the command responses. The 128 bits I was talking about, they're all zeros is what I have. Which means something is not exactly right, which I need to debug. Okay? And there's also another error that you're seeing over here, which is the SCR error, which is SCR is another register that when you read, you will get, a response back, which is again something that we're not getting. So we'll need to look at all of these things and figure out what's going wrong. But these are the steps that you'd want to use to sort of go about debugging your implementation. Okay. Okay. So let me actually look at the agenda. I guess that's what I wanted to cover. Yeah. Initialization, registers, command set, clock settings, and the commands, and debugging sensitive operations. Yes. Those are the pieces that I wanted to quickly cover. And I'm so happy I was able to cover that and not overshoot on time again. Okay, but yeah, any questions? Quite straightforward, right? Once you get the pieces, all these pieces working, then you start to see that, the uSDHC driver is not very, it's like any other driver that you're trying to implement, except that you now have a standard. You have to sort of keep consulting the standard to see whether you're getting things right or wrong. Sometimes you might end up in places where some cards do not implement the standard correctly, and that's where you might have some issues. Sometimes that's very, very rare. But yeah, but in those corner cases, some of the tidbits I talked about, checking the right bit fields, checking the right timing operations, debugging them correctly is useful. All right. Okay. So I guess there are no other questions, but so that's what I wanted to cover. Hopefully, the driver should be, if I have more time, I should be able to spend more time on this and get the driver working by the next stream. And that way we'll have more we can move forward to the next one because this is almost done. We can move forward to something like DDR initialization. How do we do that? Okay. All right. Yep. I guess there are no other questions. Okay. All right. So that's it from me. And I'll see you in the next stream. Have a good weekend. Bye-bye.